This is an FA-18 Hornet fighter jet. Like all advanced military aircraft since the 70s, it's effectively a flying computer.
Ever since the F-16 and aircraft such as that, they are totally fly-by-wire, so there is no connection between the control column and the back of the aeroplane. If you don't have the flight control computers working, the aircraft is unstable and cannot be flown by a human being.
A problem for flying computers is electromagnetic interference, EMI.
So it might be sort of broadcast antennas, might be radars, mobile phone antennas. All of that is putting out this soup of energy that then surrounds the aircraft as it flies. But in addition to that, we have the natural sources, which is like lightning. So as lightning sort of comes and attaches to an aircraft or strikes nearby, it also produces an energy which interferes potentially with the electronics on the aircraft.
It can affect everything from turning on a warning light to disabling the flight controls, causing the plane to fly in an unexpected direction or even crash.
And if we move away from the electronics, we can also interfere with the sort of explosive charges that are on the aircraft that set off things like fire extinguisher systems or maybe the bomb itself.
That's why the Defence Science and Technology Organisation, DSTO, has a suite of test facilities, including an enormous microwave chamber and a rig that replicates lightning.
You do hope that the scientists have done their job before you strap yourself into the aeroplane.
Today, the DSTO is teaming up with the RAAF. They're looking at the potential effect of radio waves transmitted from an antenna on this 500-pound JDAM. It's a precision-guided bomb. The question is, could the energy of just the radio waves hitting the plane cause electronic interference that has disastrous consequences? Imagine it. You're the pilot sitting here going about your flying business and a weapon's accidentally released because of such interference and you haven't even lifted a finger. How could an electromagnetic glitch potentially release a weapon?
So what happens is, as the energy gets in there, it can interfere with the electronics that are basically telling this bomb what to do. So, for instance, it could get into the firing circuit and then initiate it when it's not expected, or it could get into the detonator. So the detonator itself is like a little wire that you pass current through, and that heats up and then sets off the explosive. So if a current gets on there from the energy coming in from the aircraft or coming in from the side, it can then cause the same heat and then set off that explosive.
You wouldn't want that. Not all frequencies are bad. Consider the electromagnetic spectrum. At one end are gamma rays. Their wavelengths are shorter than the size of an atom. As the wavelength gets longer, we pass through to the spectrum we can see. Then it's into the infrared, used by TV remotes, and finally microwaves and radio waves, where the wavelengths are longest. It's this end of the spectrum that poses the biggest problem for fighter jets, particularly wavelengths in the 10 to 150 metre range.
The aircraft then is a nice tuned antenna. So like your TV antenna on your house at home, the antenna is designed so that it grabs onto that energy and gives you a picture on your TV set. Well, the aircraft turns out to be a perfect antenna at those frequencies.
An aircraft can be considered to act as a series of guitar strings, fixed between different points on the plane. From nose to tail, for example, nose to wingtip, or wingtip to wingtip. The length of the string determines the natural frequency that will most excite the skin of the aircraft.
And so as it grabs onto the energy, then it has that potential to get inside the aircraft and then interfere with the electronics.
When the test antenna beams the plane with a broad sweep of frequencies, a series of sensors analyses the flow of current reaching the bomb.
So there's cables coming through this pylon and then connecting onto the bomb to tell it what to do. So the aircraft acts like a big antenna and is feeding that energy down, grabbing onto that cable, and then can feed into the systems inside the bomb.
So we've got a bomb. You're exposing it to radio frequencies. It's not going to go off now, is it?
No. We're looking after you in this case. We've actually taken out all the explosives and the detonators out of this one, so it's purely sort of a test item.
They're testing the Hornet because all aircraft these days are flying through an increasingly thick soup of electromagnetic radiation, caused in part by the popularity of wireless communication these days. Also, planes are being continually updated with new technology, and so with more advanced computer processors. They operate at ever smaller voltages, making them more vulnerable to interference.
For us, it really gives us that bigger picture on what's happening in the electromagnetic environment when we change the aircraft configuration. We can see where the energy is going, so we know exactly what's going on.
The results of this test, combined with computer modelling, reveal hotspots that may be of concern.
Right, so there's a hotspot there.
Yeah, that's right, yeah. And so in that case there, we might look at that in a bit more detail just to see what is under the surface and see whether that is a safety critical system that may be interfered with by that energy. There's also energy funneling in from the aircraft and then going into where the fuel tank and that bomb is.
Yeah, the fuel tank and the bomb, not a great spot for hotspots.
No, that's right. So that hotspot is actually an unexpected sort of result. At that frequency, we wouldn't expect that. So we might look at that, take the investigation a bit further and take the bomb to a test chamber on its own and hit it with some more refined, intense radiation just to see if that would cause a malfunction.
If it's above a certain level where we think we need to implement a solution, we'll look at some sort of engineering solution to that problem. If not, we can place operating limitations on the aircraft, and that's an acceptable means of mitigating a problem.
EMI testing begins during the design phase of an aircraft, which is why the DSTO is currently testing this scale model of Australia's next generation of planes, the F-35 Lightning II Joint Strike Fighter. Ironically, it's being tested here to its reaction to lightning.
Why is this so critical? Because the F-35 needs a clearance to be able to operate in the proximity of lightning if it's to enter service next year with the US Marine Corps.
In the test, energy is injected onto the skin of the Iron Bird, as this model is known, and the team analyse how the current flows across its surface. In this case, from nose to the tail.
So when lightning hits your plane, what do you want it to do? I'm guessing you want the current to get out of there as fast as possible.
As the lightning hits the front and then flows through the aircraft in and out, the aircraft in essence becomes part of that lightning bolt. And so you want it to flow freely and not build up or sort of have any resistance, because you build up heat and then potentially you could sort of destroy panels on the aircraft skin.
But don't expect any fireworks today. This is a lower power test, so there'll be no sparks.
How do you simulate lightning using electromagnetic radiation?
What we do is we actually break it down to its component parts. So a lightning strike is actually broken up as a series of single frequency transmissions. And so by breaking that down, we can then put those through the aircraft, either one at a time and see the response, or we can do it as a simulated big pulse of energy that can then punch through the aircraft and then again look at how things are responding to that.
Strangely, the Iron Bird is metal, while the actual plane will be made of a top-secret titanium composite material, which would be less conductive.
So how realistic is the simulation, given that it's not a real plane, and in fact it's not even the real skin?
Yeah, well, what this is what we call a known quantity. So when we do our computer models, we need to have confidence in those models. And to do that, we have to gather data off of a known object. And so this skin is a sort of known object that is easy for us to model in the first instance. Also, what it does is it gives us the shape of the aircraft. So because this adequately describes that shape, we get the same sort of response.
Defence Science and Technology Organisation are acknowledged as having some of the most accurate algorithms for predicting the interference that comes from various electromagnetic sources, and in particular lightning.
Ready to go? Is the area clear?
Clear to transmit.
Okay, turning power on. We're getting good signal there. How's it look?
Yeah, that's good data. So if you can see here, Graham, the results that we're getting over here are represented by this model, which is showing the current intensity across the surface of the aircraft.
So the most intense current is in the red?
Yeah, that's right. Yeah.
Through to the blue is the least?
Yeah, absolutely.
Are there any hotspots there?
Well, in this case, it turns out there's not, which is a good thing because of the way that the test has been set up. But if we look over here on this model, so initially it's on the nose as the lightning attaches, and then you can see it on the leading edges of the wings and the tail and so forth. And so we would then take that investigation a bit further, looking at the type of equipment that is under the surface, whether it be electronics or fuel.
Right.
The outside tests find areas of concern, but they're limited to low power. Otherwise, they might cause interference to nearby electronics.
To see the effect of harsh human-made radiation on a plane, it'd be great to be able to put it in a microwave oven. Well, that's essentially what this room is, a giant microwave oven where the researchers can beam the most extreme radiation at the plane.
The most hostile environment would be the flight deck of an aircraft carrier, because there you've got the combination of aircraft landing, and an aircraft landing is when it's in its most vulnerable position, where it has a lot of its panels open, a lot of the wings are extended, and so those cables inside in which the energy can latch onto are exposed. So you have that sort of scenario with lots of high-powered transmitters nearby.
During a microwave test, energy is squirted into the chamber through antennas on the wall and bounces around the reflective surfaces. A large paddle wheel stirs the energy so the whole plane's exposed to a uniform level of radiation.
So at home, the same thing is achieved by putting your chicken on a turntable and moving the food through those energy clouds, whereas in here, because of the engineering challenges of sticking an aircraft on a turntable, we actually push the energy around using the stirrer. The paddle wheel is only good for those shorter wavelengths, the microwave, and so once we go from there, we then use the plate hanging from the ceiling.
They call it the septum, and it's part of the setup to analyse the effect of radio waves. But because their wavelengths are much longer, it's more difficult to uniformly expose the aircraft to them. So, more sophisticated computer modelling is needed.
So that first screen, we're seeing the computer simulation there of a plane flying in the air.
Yeah, that's right. When there's about 3 of those sort of hotspots on the screen, then that's sort of a wavelength. And so the aircraft is a third of that. And so that's where we're talking about that the aircraft is a comparable size to the wavelength of the energy coming in.
The modelling is compared with the results from the chamber test.
And as the energy goes through, it's exciting that aircraft. So the aim is to get the same radiation of the aircraft as we are over there when it's flying.
So basically, are you sort of ground truthing the model in some sense, that if the model's working, then you should be able to predict the situation here?
Yeah, that's right. We can't actually cover the aircraft in these measurement devices and then fly it around.
They won't let you stick those green cones all over the...
No, that's right. Yeah, the airworthiness people won't let us get away with that, that's for sure.